Hello everyone, this is Rohit Maurya and this is the fifth lecture of Unit 4. And Unit 4, as we last started the column and struts of subject Introduction to Solid Mechanics. So we discussed in the last lecture, the first condition to solve the buckling or crippling load, as we discussed, is P. The formula we came up with, P is equal to pi square upon L square into AI. So that is the condition where the column or say strut is having the end condition hinged or say pinned. So the other three conditions where the end conditions for support in a column or strut is different. So we're going to start with these three. Okay, here it is. So in second condition, what are the end conditions? And joint condition is one end is fixed, other end is free. So according to this case, this curved column or strut having one end is fixed here at O point and other end is free at A point. So in case we apply our load P at A or say at free point end of a beam or column, then this column or strut deflected. Okay, so the value we assumed to be deflected maximum at free end is small a. Okay, then again, as we did in the first condition, we put a point where we cut the section to find the bending moment. So we cut a point here. Okay, we cut a point here, and again we have a vertical distance x and we have a vertical distance x and horizontal distance y. So according to point A, we have a coordinate again xy coordinate of this point. So we cut the beam or strut at this point xy coordinate and try to find the bending moment generated due to the load P. So we can easily find the bending moment at this point according to load, which is the load and the tangential distance between this. So what are the tangential distance? We know that the maximum deflection due to load P is small a, and the horizontal distance we assumed is y. Then the left space having the distance a minus y, which is shown here. So we easily find the value of P, bending moment, which is P into a minus y, and as we did in the last condition, we take the value of bending moment in the negative side due to the reason the load is rotating downward direction. So again we have a same equation, ei d2y upon dx2 is equal to mu, which is the bending moment, is equal to p a minus y is equal to pa minus py. So in this condition we didn't choose the value as it is as a negative, because the reason behind he chose that, because in first condition the bending moment generated is having the rotational point in the beam in the downward direction. But in this case what happened is, in this the moment generated due to y point is alongside downward diet, but it's one directional, not along the vertical axis and going through the middle part of it. So that's why we didn't choose the value in negative, as I already said before. But with this particular condition we didn't choose it as negative. Okay, so what happened, we multiplied the value of P and we separated the part of y as we did it earlier, divided the ei in the whole equation, then we converted this part as we did it before. We have a d2y upon dx2 plus alpha square y, where alpha square is p upon e, and then here it changes. We have a pa upon ei. So we have a different kind of a partial differential equation of second degree. Then how to solve it? So in this condition, if we have a partial differential equation in this form, then the solution is this way. Solution equation is this: y is equal to a sin alpha x plus b cos alpha x plus this part pa upon ei divided by alpha square. Then what we have? pa upon ei multiplied by alpha square in division, and we already have the value of alpha square, which is p upon e, and by placing the value of p upon ei in here, then p upon ei and p upon ei cancel out and remain is a. Then the final solution equation is y is equal to a sin alpha x plus b cos alpha x. Okay, now do the solution. Now putting the boundary condition: when x is equal to 0, y is equal to 0, then b is equal to minus a. If we put x is equal to 0 here, as we can see here, if x is equal to 0, y is already become 0. X 0, y becomes 0, then value of b becomes minus a, because sin 0 is equal to 0, then this part becomes 0, and cos 0 is equal to 1, then it's remain b, and y is already 0, then the value of b is equal to minus a. The second boundary condition is when x is equal to 0, dy upon dx is already 0. dy upon dx is the value of slope. That means if we do the x is equal to 0, the slope is here is 0. Okay, at the support, fixed support. Then what we have to do? We have to differentiate the equation of y, and by differentiating we have the equation a alpha cos alpha x minus b alpha sin alpha x is equal to 0, and we put the value of x0 in here, and by putting the value of x0 in here, we have sin 0 is equal to, then this part becomes 0. What we left with is this part, a alpha cos alpha x, and we have x is already 0, then cos 0 is equal to 1, then what remains is a, and then a becomes 0 here. Okay, now in that condition we put both of the condition, a is equal to 0 and b is equal to minus a, and in this equation. Okay, then we have y is equal to minus alpha, this is a value of b here, minus alpha cos alpha x, and the value a is already been 0 here, this part becomes 0, and the value of b is equal to minus a, and or a is already been exist in the solution equation. Then we can take out a from both of the parts, then we have this equation, y is equal to a 1 minus cos alpha x. Okay, then the last boundary condition is when x is equal to L, y is equal to a. You can easily see that when x is equal to L, y becomes a, then put it in this equation, y is equal to a and x become L, then a cancel out, 1 cancel out, then we have remain cos alpha L is equal to 0, and we know that at which value of L theta where cos becomes 0, which is pi by 2, and by putting so we have a value of alpha. And similarly, as we did in before, we put the value of alpha in main general equation, which is alpha square is equal to p upon ei. Then we have p is equal to alpha square ei, and the equation converts to pi square ei upon 4l square. And this is a case where one end is fixed and other is free. And same in the same procedure we follow and solve this equation where both ends are fixed, and in case we have generated moment and the equation converts to m upon ei, and here this third part becomes m upon p, and we have a same procedure to solve by putting the value of AND condition x equal to 0, y equal to 0, p becomes m upon I, x equal to 0, what slope is 0, then equation converts to and give value of a is equal to 0, and putting both of these condition in first equation, solution equation, then we have this equation, and lastly we put the final boundary condition which is x equal to L, y is equal to 0. Then we have again cos alpha is equal to 1, and in this case when did the value of cos becomes 1? When the value of theta becomes 2 pi, and we put it here. Then we have a value of alpha which is 2 pi upon L, and then we have a crippling or buckling load is P is equal to 4 pi square EI upon L square. Okay, and then we have last condition, one end fixed, other end hinged or pinned. In that case we have again choose a point, find the bending moment which is minus py, and we have a support reaction here R. This is a P vertical load and a support reaction, lateral horizontal reaction which is R. And why did we choose it here and not in the first condition where both of the end is hinged? Because in this case the fixed one end is fixed and another is hinged, and the remaining lateral force cannot be equal, and or we can say the net resultant force cannot be equal, and that's why we have a value of horizontal reaction, and which we put it at this point as the value of R. Then both of the forces considered P and R, and along with this point the bending moment generated due to R is equal to L minus N, because we choose the distance x from support reaction. Then we have converted again as we did in the last, divided EI, assume alpha square is equal to P upon EI, and then we have a R upon EI alpha square, and putting the alpha square value here, then we have a solution of R upon P L minus X, and again we did the boundary condition apply, x equal to 0, y is equal to 0, then we have a B is equal to minus RL upon P, x equal to 0, slope is equal to 0, put it all the values here by differentiating the equation, then we have a value of A is equal to R upon P alpha. Okay, then both of these equation A or B put it in the generalized equation and solve it, and put the last boundary condition x equal to L, y is equal to 0, then we have this equation tan alpha L is equal to alpha T. Okay, and to solve this condition, we directly put the value of this part. Okay, we directly put the value of this part, which is 4.49 radian. How can we do that? We actually did perform the various experiments on this particular case and find out that the case where the value of this converts to be as 4.49 radian. Okay, then we have the value of alpha is equal to 4.49 upon L, and the alpha value put it in the first equation, and then we have a P is equal to alpha square EI, and putting the value of alpha, then we have 20.2 EI upon L square, and we converged in the value of pi by means we convert to 20.2 into two parts, 2 into 10.2, and 10.2 can be written as pi square. Okay, then in the next part we have a equivalent. So what we did, we have a 4 equation of crippling load for 4 different end conditions. So to find the generalized equation by putting a generalized value of something. So we generalize the equation for different kind of end condition, and we can easily do this by seeing that in all four cases we have a length due to which the value of crippling load changes. And so what we did uh, generalize the formula in this form: P is equal to pi square EI upon LE square, where LE is denoted as a effective length, and effective length can be converged or expressed in different end condition of a different loading in a different kind of beams. So as we can see that in first condition, the effective length is L for both end is hinged, and second case, one end is fixed, other is free, L is equal to 2L, and in third case, though both end fixed, the L is equal to L by 2, and in last case, one is fixed, other is hinged, L is equal to L upon root 2. By means this, if any of the case we put the value of sequential in this formula, then we converge this formula in their original way, as we did find in their consecutive consecutive derivation. Okay, then we have limitations of Euler formula. These are basically known as Euler's formula. Okay, then the limitations of the Euler's formula. Now if we know that P is a crippling load, then we can easily find the failure stress or critical stress. Okay, if we know the cross-sectional area of a beam. So sigma c is representing the critical stress, which we can find by dividing critical or crippling load upon area. We already have the formula of P, which is pi square EI upon LE square, and A is already there. And what we did is we place the value of I, which is moment of inertia. Okay, and by doing so we cancel out the value of A, and last we have a formula converged into pi square E upon LE upon K to the whole square. Okay, where what is K? K is a radius of gyration, and L upon K is equal to slenderness ratio. This slenderness ratio defines how much beam have its cross-sectional width to the length. By means is that due to slenderness ratio we can deduce that how much it is in width than it's in length. Okay, then here we have a curvature of this equation: critical stress to the L upon K, where L upon K is a slenderness ratio. So according to slenderness ratio, the critical section has to be at this B point. Okay, and beneath or under this area, or we can say if the value of slenderness ratio goes down, okay, then whatever the value consisted here, the Euler's formula cannot work, which is a short column. By means that if the slenderness ratio is less, okay, this means that the column is short compared to its width, compared to its thickness, whatever you use the term. So in this region where the slenderness ratio goes less than a critical stress condition, then Euler's formula cannot work. Okay, and it comes in a region of short column. Okay, and for structural steel where the critical stress of a concrete steel beam, not a concrete, critical stress for steel beams is to be taken as 320 MPa, and if the value of Young's modulus of a steel beam is 205 GPa, then we have a L upon K is equal to pi under root E upon sigma C, and by putting the value of these two values, we have a 79.5, which is almost 80. Then we have, thus the Euler's formula is applicable for slenderness ratio greater than 80 for steel hinged at both the ends. So we can easily say that in case of both ends are hinged, okay, of a steel member, steel column, then the slenderness ratio has to be lie between 80. Okay, thank you.